Welcome to this lecture series in real analysis. In this lecture, we'll look at some applications of the intermediate value theorem, and let us recall what is the theorem. So it says that suppose we have a continuous function where the domain is an interval. It could be any interval, open, both closed, semi-closed, semi-infinite, anything, but just an interval. And an interval can be characterized as convex subsets of R, meaning those subsets of R which have the property that if you choose 2 points A and B in them, the entire closed interval or everything in between A and B is also contained there. So that is a defining property of intervals. Alright, so if we choose a continuous function on an interval, then its image is also an interval, which can be read as follows. If f takes two values, then it takes everything in between. That's what the intermediate value theorem says. If f takes two values, then it takes all the intermediate values also. Okay, so now let us continue. Here are some problems for practice. And now let us get started. So we have our first result, which is very, very nice. We have a continuous function from the closed interval 0, 1 to itself. We want to show that there is some point in it which is fixed by f. So f is not disturbing that point, it is eating that and outputting the same thing. So that's the thing, and let's see first a graphical reason for it and then a formal proof. So let us draw the graph of the identity function, meaning the function which takes x to x. So that would be, I think, this thing. Yep. So that is the graph of the identity function. We are only interested in the region 0 to 1, so let me try to mark that out too. Now, suppose f0 were already 0, then we have found our x. Alright, so we may assume that f0 is non-zero, and therefore f0 must be some positive number in this interval. So let's say f0 is somewhere here. We are trying to see what the graph of f looks like. So let's say f0 is somewhere here. Okay, similarly, if f1 equal to 1, then we were already done. So f1 can be assumed to be less than 1 in the adverse case. So let's say f1 is somewhere here. But since f is a continuous function, the graph should therefore, intuitively speaking, intersect this line. And wherever it does intersect that line, you just come down and report that point as your fixed point, because at that point, the value of the function is matching the value of the identity function, but the identity function clearly fixes everything. So that's the main idea, and we will just execute that idea. So here is just kind of the main step. Define the map G from the unit interval to R as this thing. Okay? And a restatement of the problem is that we want to show that G x naught equals 0 for some, and let me write gx equals 0 for some x in the domain. Right, so if we are able to find such an x, then for that x we must have fx equals x. Because if gx is 0, then fx should be equal to x. So this is our goal. This is what we will achieve using the intermediate value theorem. How? First of all, note that g is continuous. G is continuous because it is a difference of two continuous functions. Or you can also think of it as the sum of two continuous functions, of course. And in the algebra of continuity, we saw that sums and differences and products of continuous functions are continuous. Okay, so g is a continuous function and hence amenable to the intermediate value theorem since it is defined on an interval. So now we have g0 is what? G0 is same as f0, and g1 is same as f1 minus 1. Okay. Now if f0 were equal to 0, we were already done. So we may assume that this is strictly positive, f0 is strictly positive. Because what are the other choices for f? F takes values in this interval, and if f0 is non-zero, f0 has to be positive. Alright, so here I have to write a few things, but I am not writing them. I'm just saying that if f0 were 0, then we were done. So we may assume this happens. We are not claiming that this is necessarily true, because the function f could have taken the value 0 at 0. Who is stopping that? So here the hidden thing I am not writing but saying is that if f0 were 0, then we were done. So we may assume this is the case. Alright, similarly, if f1 equal to 1, then we were done. So we may assume f1 is not 1, but then f of 1 has to be strictly less than 1, and hence this has to be strictly less than 0. So we may assume that this is strictly less than 0. Okay? But now, g is a continuous function which takes positive value at 0 and negative value at 1. And hence it must vanish somewhere in between, in fact, strictly between 0 and 1. So g must become 0 somewhere by the intermediate value theorem. And that shows that fx equals x for some x. Alright, so it's a very simple proof. I'm sure you have seen this kind of thing even in high school, but perhaps the proof during those days was not rigorous. Alright, so we move on. So the next thing that we want to do is show that every odd degree polynomial has a root. As a real root. When we say odd degree polynomial, we will mean odd degree real polynomial, and when we say root, we will mean real root. So let's recall some definitions. So a function from reals to reals is called a polynomial of degree n, where n is a non-negative integer, if there exist real numbers a0 up to an, with an non-vanishing, meaning an is a non-zero real number, such that for all x, px is equal to that thing. Okay, and this term an is called the leading coefficient, and this whole thing is called the leading term of the polynomial. Okay, so I'm sure you know these definitions, and we say that a point a is a root of p if p vanishes at a. Now, not every real polynomial has a real root. So if you define your polynomial via this equation, this does not have any root, meaning it does not have any real root. It has complex roots, but it does not have any real root, while it is interesting that you take any odd degree polynomial. This was an even degree polynomial. The degree of this polynomial was 2. But this is an even degree, this is an odd degree polynomial, and this has a root, and that's not trivial. And this is what we will show, that every odd degree polynomial has at least one root. So here is the formal statement. We have an odd degree polynomial. We have an odd degree polynomial p, and we want to show that it has a root. Okay, so let's fix some notation. Let's say px is for all reals. Okay, but it will be more convenient to write it in the following way. Right? That's what the thing is. Maybe, sorry, this is not 1 to n, this is 0 to n minus 1. Right? Okay. And we may assume that the leading term, or rather the leading coefficient, is positive. So when we had written px as that, there are two cases. Either this thing is positive or negative. I'll just argue in the positive case. A very similar argument will also go through in the negative case. Okay, so px is that thing. And yeah, so which we can also write as, or in a separate line. So note that, or we have so all we did was we deliberately pulled it out. So inside we will get this. just some algebra. And this is valid only for x non-zero because we are dividing by x. Okay, something is bothering me. Yeah, so it's fine. Now the point is the following. If x is very large, this term kind of doesn't really matter. It becomes very small. If x is big, this is very small, therefore this is very small. So the large scale behavior of the polynomial is controlled only by the leading term is all that this proof is about. If you just look at the leading term and see what it does on large scale x, meaning x which has large magnitude, so if you feed here large positive integers, you get something positive, definitely. And if you feed small, positive integers, by small I mean very, very left to the origin, you get something negative. And whenever you are very large, when the magnitude of x is very large, this does not matter, so this term remains positive. So therefore the sign of the value of px is governed only by the leading term if x is sufficiently large. And therefore px will take both positive and negative values, and that is this proof. That's what this proof is. So let's execute this last step. So we have for some positive integer m, we have p of m is which is greater than equal to, and I will explain this. So I need to explain this inequality. Very, very simple. All we are saying is that 1 plus summation xi, let me say alpha I is our real numbers. This is at least that much. It's completely trivial what I'm writing. Okay, so we have that. But now here is the point. If m is a very large positive integer, then this is very small, and therefore this is very small. So if m is sufficiently large, then so this is all that you need to justify, that if m is very large, then this thing is less than some convenient value. And you should be able to do this immediately by now, because if m is large, then the infimum of these numbers go to 0, and hence same is true for this. And since there are only finitely many things, you can say it for all of them. So just justify this line. And therefore, thus for sufficiently large m, we have Pm is at least this much. Just use this bound to every term. So what is this? This is a half, because there are n terms, and every time we are adding 1 by 2n. So this is a half, and hence this is a half. So this thing is equal to half of this, but this is a positive thing, right? Because an was positive, and hence this is positive, and hence this is positive. So for sufficiently large integers m, we get positive value of the polynomial. And so far we haven't even used the fact that n is odd. This holds even for even degree polynomials. This argument has nothing to do with oddness, but we use oddness here. And for sufficiently large m, we have p of minus m, and let me use a different color, p of minus m, which is nothing but, by definition, is equal to that much, which is less than equal to. So what happens here? The whole point is this is a negative number because n is odd. Minus m is negative, and hence since we are exponentiating with an odd power, this whole thing is negative, but an is positive and hence this is negative. So here this is negative, and therefore this time when we make these sufficiently small, meaning each of these have magnitude at most 1/2n, the same bound we are using, the inequality this time will go the other way because of the negativity of this. And this right thing is equal to minus half of an m to the n, which is negative. So for sufficiently large m, p of minus m is negative. So what we see is that the polynomial p takes both positive and negative values, and that finishes the proof that p has a root by using the intermediate value theorem. All right. So this has some corollaries. Now we can talk about square roots and cube roots and so on. I mean, we could have talked about them earlier, but now it will be more potent. So the theorem is, for each positive integer n, this map from non-negative reals to non-negative reals, which exponentiates to the nth power, is a bijective map. So to show bijectivity, we need to talk about injectivity and surjectivity. So injectivity holds for algebraic reasons. Injectivity is, you just suppose fx equals fy, then this must be 0, which implies what exactly? I always get confused here. So yeah, so this is x to the n minus 1 plus x to the n minus 2y plus dot 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 plus y to the n minus 1, that thing. So I'm just using the factorization of this. This is as long as x and y are both non-zero, or at least one is non-zero, this will be positive because we are using only non-negative reals. So if x and y are both 0, then nothing to do, then x is already equal to y. So let's assume at least one is non-zero, and hence this is positive. But the zeroness therefore implies that this part must be 0. So I forgot to write that this thing is equal to 0. Right, so what are we doing? We want to prove injectivity. So to do that, we will first assume fx equals fy for some x and y lying here, and end up showing that x is equal to y. But fx equals fy means this is the case. Sorry, fx equals fy means this is the case, which means this is the case. But if x is not equal to y, then this is positive. But this product is 0 implies this is 0, which implies x is equal to y. So you can go by contradiction. But anyway, so this establishes injectivity. So injectivity holds purely for algebraic reasons. But for surjectivity, first note that f is continuous, and f assumes arbitrarily large values, and f assumes the value 0 at 0. So f is taking the value 0, and f is taking arbitrarily large values. So by the intermediate value theorem, it will take all the values in between, and therefore it will take all non-negative reals in its image, and therefore f is surjective. So f is both injective and surjective, and hence bijective. Great. Immediate corollary is the following. For a positive integer n and a non-negative integer x, there is a unique non-negative y which satisfies this equation. And notationally, we write y as x to the power 1 by n, or we also use this notation. Okay. When n equals 2, we don't write anything. We just simply write this surd, this symbol, which is square root. So note that here we do need positivity of x to get a unique positive y, or rather non-negativity of x to get a unique non-negative y. Because, for instance, suppose n were 3, then you would have if n were equal to 2, not 3, if n were equal to 2, then minus 1 square is 1 as well as 1 square is 1. So to get uniqueness, you need to force this condition. If you drop this inequality, then there may be 2 different values. So yeah, I may have said something wrong here, I have a feeling, but anyway, I'm sure you understand. Fine, so this is one corollary. And here is the exercise. For odd n, this map, which is defined on entire reals, is bijective. Right? So that is what I was trying to say here. If n were even, then you may have two different nth roots, so to say. But if n is odd, then you have only one nth root. So just please make sure that you understand all three statements. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.